So can you see my screen, example 4.3? Anybody?
Yeah, we can see.
All right, thank you. All right, so let me do some introductory remarks here before we begin. So again, you should have all the data you need for the lab section. I did post the F prime C values as well as the data for the beam test, delta versus deflection versus the pressure. So you should have everything you need to start working and then even finish your lab report and presentation, with the exception of the shear reinforcement. And I said once we get to number 8, chapter 8, we will definitely finish that. So what I'd like to do today is I'd like to finish the examples in chapter 4. We have I think 2 examples. And then after that, we will be ready to design the beams in our project. So what I will do next week is we'll start working on the design of our beams in the building. Okay, that's why I want to finish the examples today, and then this way we can move to the next step. Any questions from anybody? Any concerns? Any comments? Any questions? All right, so let's begin. Last time we did example 4.2, I believe. We did not do 4.3. Is that correct? Anybody? I think we started it, then I stopped it because I think I said we don't have enough time, I believe.
Yeah.
Right? Okay. Thank you. So we'll go ahead and begin from the beginning. Example 4, and then I'll take attendance before we finish tonight, of course, today. So design a rectangular beam for rho equal that. And like I mentioned in the lecture, make sure you do all these examples, please, because every example have a different thing attached to it. Like in this example, rho is given to us. The one before, that wasn't the case. So make sure you do all the examples. It's going to help you a lot understand the subject. And it's really easy. It's not bad at all. So it says design a rectangular beam for a rho equals 0.012 approximately. Notice that rho is almost always around 1%, because this is in plain English 1.2%, right? If you take this number times 100, it's 1.2%. So it's around 0.01, 0.009, 0.12, and it's around that number. And mu is 600 Gibbs foot. See, notice that in the previous example, he gave me dead load, live load, and we calculated M sub u. But here he gave me M sub u. Doesn't matter. He's given me also F prime C 4,000 and Fy is 60,000. Assume mu includes beam self-weight. So we don't have to worry about the on weight of the beam. He's saying it's already been accounted for in this moment, in the mu. So assume phi equal 0.9, and then mu over phi bd squared equal to this equation. We've seen it many times. So you start substituting here. Mu is 600 given. But of course, I multiply by 12 and 1,000 to get it in pound foot, right? And pound inch, because 12 inch per foot, and this is pound per Gibbs. 0.9 phi. B and D, I don't know B and D, because I'm designing the cross section. Equal, rho is given, 0.012. Fy is given, 1 is constant. Everything here you know. So look at this one huge equation with 2 unknowns, B and D. Of course, I cannot solve that. You need 2 equations. So if you simplify this, BD squared equal 12,427 inches cubed. Be careful with the units. That's why we converted to inch per foot and pound per kib. So one equation with 2 unknowns, I cannot solve, but if I assume 1, I can calculate the other. And from practical experience, a lot of our beams are 12 inches wide, 14 inches wide, 16 inches wide, and all that stuff. So we can assume, we go B times D here. I assume B as 12, 14, and 16. If B is 12, you can get D, right? D equal 12,427 divided by B, square root of that. So that comes 38.18, 32.18. If B is 14, D is 29.79. If D is 16, B is 16, D is 27.87. Okay, so we're gonna shoot for the middle number. Try a beam with B equal 14, and then of course if I round up this D, make it 30. So it will be B 14 and D is 30. And then remember, I always said that the center line from the center of the bar to the bottom is either 2.5 or 3 inches. In this case, he added 3 inches. So 30 inches plus 3 is 33 inches. So we're gonna try that beam, all right? So how did we get this? By knowing rho, because if I know rho, I can do this. If I didn't know rho, I cannot do that. But he gave me rho in the problem. Okay, this whole thing here, instead of doing all that, this is really mu over phi bd squared. It said this is equal to rho. This is equal rho of this equation can be read directly from this table, A13 643.5. Okay, so I'm gonna skip to that and show you that now. Okay, so I want to remember that 643.5. Why? Because rho was given as 0.012. All right, so let's see how we do that. I'm gonna reshare screen here. Share a new screen, and I'm gonna go here. So let's spend couple of moments, couple of minutes on these tables, so we can address them. This is from the back of the book, okay? This is from the back of the book. Sorry, am I gonna get that? And I want you to be familiar with the back of the book, guys. Let me turn my...
Professor, I have a quick question.
Yes.
All of the tables just they all come from the is it the ACI 388?
Yes.
Okay.
All these tables are from the ACI code, okay?
Yeah, but is there, I know because there's different, is it one manual or is it just the ACI 388?
318.
318. Okay.
Yeah. So yeah, the ACI 318 has some tables in it, and there are some other documents like there's some more ACI document that gives you even more information. But this is coming from there, and of course they calculated those based on the formulas we just mentioned, and I'll show you that in a second.
Okay.
So it's nothing magic about it. Is somebody did the calculations by changing numbers, and then they came up with the table, really.
Okay. So in the field, when we refer to things like this, we would be using like is it the ACI 318?
Yes, usually in design offices you will find manuals and 3-ring binders and all that. Has a lot of these information in it. It's all based on the ACI and all based on those equations, of course.
Okay, thank you.
You're welcome. Okay, so I'm gonna take a couple of minutes to spend on the back of the book here since I have them displayed. So table A1, see, we always refer to those tables. If you have F prime C, let's say 4,000, you can get the E sub C, which is the modulus of elasticity, right away equal to this 364,000. Of course, E sub C can be calculated equal to 57,000 square root of F prime C. Remember? So you put square root of F 4,000 times 57, you're going to get that number. But this is handy. you can use it if you need to. Okay, another table A2 in here. If you know your bar number, number 3, number 4, and remember we look at that, you know the diameter of the bar. And we said up to number 8, the diameter equal the bar number divided by 8. So 3 over 8 is 0.375. 4 over 8 is 0.5. 5 over 8 is 0.625. 6 over 8 is 0.875. 7 is this and 8, but if you go 9 over 8, you're not going to get this number. It's going to be close, but it's not going to be that number, so you will read it from here. Okay? Now, also it gives you this cross-sectional area of this number. For example, number 3 bar, the area is 0.11 inches square. Number 4, the area is 0.2 inches square. We already used these tables, but I'm just kind of... Another column here is the weight, unit weight in pound per foot. Let's say you're using number 4 bars. Every foot of a number 4 bar weighs 0.668 pounds. That's what this means. Why is this important? We're not going to use it in this class, but what happened in real life, you could be working for a contractor, and the contractor is going to give you the set of plans, and he's going to tell you, calculate for me how many tons of steel is on the job, because they usually order the steel by ton, not by bars. How many tons of steel? So you're going to take all the bars, like let's say number 4 bar, you have 100 number 4 bars, every bar is 10 feet long. So you can calculate the weight of those and then get it into pounds and then convert that into tons. Right? So that's when this one will help you. Okay, the next table is, it calls about the welded wire fabrics, welded wire sheets. Remember we said we're not going to use that, but it's here. We didn't worry about that. You don't use it a lot in buildings. This is important here. So this table, if you know, no, that's still about welded wires. We don't need that. This is one here, A4. A4, again, the bar numbers. Notice that he didn't list number 3 bars here, because we very seldom use number 3 in beams and all that. It's a small one, usually used for stirrups and ties. But what this table does is, let's say you have 5 number 6 bars. See, number 6 bars, 5 of them, the area of 221. See that? Number of bars, 5 bars, number 6, 2.21 inches square. Look at the unit, that's the area of the bar. So this gives you the group of the bars. Of course, you can get the same thing. You can go to the first table and you take the area of one number 6 bar, multiply it by 5 or whatever. Bar number times the number of bars. But this gives you a table right away, and we will use that a lot. All right? And then this continues 11, number of bars, 12, and so forth. So you get that. Okay, so there's we're gonna refer to this a lot today. Minimum web width inches for beams. Remember we covered that. So once you know, let's say you want to know what is the minimum width of a beam that's gonna fit the number of bars you selected. So for example, if you choose 4 number 6 bars, the minimum beam width you need is 10.5 inches. See, minimum beam web width is in inches. So 4 number 6 bars, you need 10.5 inches of beam. So if your beam is 12 inches, you're okay. If your beam is 9 inches, you're not okay. And the idea of this minimum width is we want to make sure the spacing between the bars are per code. Okay, so this is a very important table here. Okay, this is also important, the areas of bars in slabs. Next lecture, we're going to cover the one-way slab, how we do the reinforcement. You will see areas of bars in slabs. inches square per foot. We're gonna take a 1 foot strip of the slab and design that, and then so you will see that once we get the AS, we're gonna come here and then pick up. Okay, we're gonna have like number 4 at 8 inches. The area is gonna be 0.29. But I will illustrate when we get there. But this is especially for slabs. Okay, not for beams, for slabs. We'll come back to that. Okay. All right, this is another very important table. So that's why I want you to spend some time on those tables, guys. This table is, if you know F prime C, that's the F prime C, 3,000, 4,000, 5,000, 6,000, and Fy is these. See, when we say grade 40, that's 40,000 PSI, or this is in megapascal, but we're not doing metric. Grade 50 is this. Grade 60, that's where we're gonna be all the time. We don't use these for structures. Grade 60 is 60,000 PSI. So we're gonna be in this row and one of these columns. Most of the time is this 4,000. In this course, you're not gonna see 5,000 or 6,000. You're gonna see either 3 or 4. So 4 is most of the time. Remember, we did so many examples now when we said, okay, row minimum, and we had equation to calculate row minimum. Look at this. You can easily, row minimum for flexure is 0.0333 for 3,000 or for 4,000. Okay? And remember, we don't have a row max here. I told you last time. There is no row max. But the row max is this one right there. Is row when epsilon t equal 0.005. That is the row max. So you can, make a note of that. So your row max for 4,000 is 0.0181. Okay? The other two, remember, we're listing a 0.004 because, remember, 0.004 to 0.05, we can still use that beam. So he gave us those values. And then so forth. Row balance, this is when the concrete will crush and the steel will yield at the same time. And we said we use it as a benchmark, so we have row balance. And of course, we have a huge equation to calculate that. But instead of doing that, just look at here. Okay, so that's what that is. So that's very important table. And this is the important table we're going to use tonight. Okay, so notice first of all, Fy is 40,000, and then F prime C is 3,000. And then in this table, we have rho versus mu over phi BD square. Okay? So we will illustrate that in the example. So this is what that is. So let's go to the next one. This is continuation of that. Make sure you are in the right table. Look at this table, A9. A9 is F prime Y, Fy 40,000 and 4,000. Okay, same thing. We need the 60,000 for us. This is for 50,000. See? 50,000, 3,000. But ours is 60,000 and 4,000. So make sure you are there. So this is 60,000, 3,000. That's still not ours. Is the one I skipped. Okay, so this is the one. 60,000 Fy and F prime C is 4,000. So make sure this is the first thing you're gonna check. And then you follow your row. Can somebody tell me what our row is? 0.01. Anybody? What was that? 0.0123?
0.012.
12, okay, 0.012, 01, okay, right there. So this is 0.012. So 0.012 is right there. You see my mouse?
Yep.
Look at that. Look at the value, 643.5. Okay, 643.5. What is that? That's mu over phi bd squared. All right, so as simple as that. Now let me switch screens. So there you go. So if I look at my example again, so he's saying that instead of doing all this calculation, this is really not, you can read it 643.5 from the table. Okay, and you will see that in that. So bottom line, I can say mu over phi bd squared. Because I know my rho is equal, right here, I can put 643.5 right there instead of all this. And then you have b and d squared are unknowns, and you solve for that. Anyway, we're going to see it again in a minute. So if we choose that, like I said, then that's what we're going to be. So now AS equal rho BD. AS 0.012, B is 14, and D is 30. That's my area of steel. That one of the tables I showed you, you take that area of steel and you go there, you will find 4 number 10 bars. It gives you 5.06, just over that. Okay? So now, you remember our rho, we assumed 0.012, but now my area of steel, I modified it. So my rho is going to be different. 5.06, rho equal AS over BD. 5.06, 14 and 30, 0.01205. See that? Because I upped it a little bit. Why did I do that? Because there's no way I'm going to go to the table and find exactly that number. I'm going to find something close to it. Close, it's equal or higher, of course, so we get that. So this one is greater than rho minimum. Again, from that table I showed you, rho minimum was 0.0033. So we're okay. And rho is less than rho max, 0.018. Again, rho max was not listed, but it listed rho corresponding to epsilon t of 0.005. That's that number. If your rho is less than rho max, then phi is 0.9. Okay? So then you say this is the equation, mu equal to that. Okay? Equal to that. So this is the equation. It's okay, let's do it this way. Next example, we're going to look them up in the table. So mu over phi bd squared, you just 0.9, b is 14, d is 30 square, rho is this number, fy is this, and plug all these numbers. But bottom line, in the next example, you don't have to do all this. You can just go to this table and look up this number. Okay, but for the first examples or two, go ahead and do them, and then you'll appreciate the tables. So if you do that, then it comes out 610.1 Gibbs foot. So if I design a beam 14 inches wide, 30 inches D equal 30 inches, and I put four number 10 bars in it, then the moment that this beam can carry is 610 Gibbs foot. What is my moment? My moment was given in the problem as 600. So I exceeded that. So that means my design is fine. See, greater than 600 Gibbs foot, so it's okay. And then you do the sketch. Here you go, 14 inches wide, 30 inches D. This is 3 inches. So this made it 33. Now this could be 2.5, remember? But if I put it 2.5, this is gonna be 33.5 inches. It's not nice. Just your beam is 14 by 33, not 14 by 32.5. Who cares? Half inch is nothing. See, that's the difference between 2.5 and 3. So you can round up the numbers. And there's the 4 number 10 bars. All right? And then how you get these spaces? You said, okay, I have 1, 2, 3, 4, 5 spaces. So again, you say if I make this 2.5 inches, this 2.5 inches, then I have 3 inches in the middle. Okay? And then we are going to discuss what is this minimum distance. Cover that. Again, that's 2.5 or 3 inches, just like the bottom here. but most of the time you're gonna be 2.5. Don't be too wide because you want to be close to the surface. Now, another way, instead of doing this to calculate M moment, then you alternatively, phi Mn can be calculated by doing this. A is equal AS Fy 0.85 B times D. Remember, we've seen that. So, and then you can use this equation. VAS Fy D minus A over 2, plug everything here, you know everything. And then you get the same answer. Look at that, 610.5, 610.6. Very close. Now, okay, so we did that. Now, how do I know the spacing between these bars are okay? You look up that table I just showed you a minute ago, table A5, you say, for 4 number 10 bars, what is my minimum beam width? You're going to find beam minimum is 12.9. But your width is 14, so you're okay. All right, so that's that. Any questions? Again, the problems are very simple, but I want you to do all the examples, because then, yes.
Yes, sir. So I understand that you said that this is not on Beachboard, but it's in our books, correct?
Which yes, it is in the back of the book. Absolutely, all these tables.
Okay, but I'm talking about the slides that we're seeing. It's not
this. The slides, no, the slides are in.
Right, but
it's in the book.
It's in the book.
Like absolutely, all the examples are there.
Okay, and basically, is there? I see that you just showed us 2 different ways to do it. To calculate it, is there like a specific way that you prefer us to do?
Yes.
Okay.
Yes. Good question, and that's gonna be the next example. Next example, we're gonna do that. Okay. Any other questions? All right. Good question, though. So let's go to the next example. Example 4.4. It says select a rectangular beam for a 25-foot simple span. I mean, simply supported. And a dead load of 2 kips per foot. See, that's the dead load, not including beam weight. So the beam weight has not been included here. Okay? And a live load of 3 kips per foot. Use again, concrete strength is 3,000 and grade 60,000. So when I go to those tables, MU over phi BD squared, I need to be in this table, not the one I just used, because this is 3,000, 60,000. And then the problem said use rho approximately 0.18 F prime C over F1. So this is a good estimate. If we don't know the information, like when we do the design in the project, this is a good estimate to use. Where did that come from? Experience. Okay? So if you're doing your project, you know, nobody's going to tell you, oh, given rho equal that. But if you want to estimate, this is a good estimate to do. Okay, we'll talk more about that. So 0.18, F prime C is 3, and 60 is that, so 0.009. Notice rho, like I mentioned, is close to 1%, because this is 0.9%. The one we just did was 1.2%, so 1% is roughly closed. Okay, so this is another way. See this? Assume a beam weight of 400 pounds per foot. The other example we didn't assume. The last example, the beam weight was included. The one before we didn't assume, but we assumed the width and depth based on like 10% of the span, and once we found the cross section, we got the weight. This is you assume the weight right away, but look what happened now. So if I assume the 400 pound per foot, that's the dead load of the beam. So that's 0.4 kips per foot, right? So he also told me that the dead load is 2 kips per foot. So I need to add the on weight of the beam, which is 0.4 to that. So when I do my WU is 1.2 dead load plus 1.6 live load. 1.2 dead load is what? Is the given 2 kips per foot plus the on weight of the beam, which is 0.4 kips per foot, plus 1.6 live load is given as 3. So it gives me this number. I calculate the moment, WL square over 8. Please watch for the units, is 600 kips foot. Okay? Then look at this. mu over phi BD squared equal to that from the table. Why? Because I know my rho. Rho is 0.009. You're going to go to that table and go backward, read the mu over phi BD squared. Okay, so if you do that, then you're gonna find as 482.6. Okay, 482.6. Okay, let's do that. I'll do it one more time and then we won't do it again. So let's go back to that table and see. Somebody write this number down, please. So 482 points. No, it's 0.009. Then we'll read that. Okay. So let me switch screens again. So first thing, I need to be in the right table. See, this is 60,000 and 4,000. Mine is 60,000 and 3,000. There you go. So this is that. See that? 60,000 and 3,000. My rho is 0.009. So where it is, it's right there. Note, be careful which one to read, to the right or to the left. Okay, so look here. So mu over BD squared. So when you take rho, you're going to read to the right. For this row, this is that column. For this row, that's that column. So 0.009. So I'm going to read this. It's 482.6. That's my mu over phi BD squared. What was our value, anybody? 482.6. Any question before I flip the page? So you understand that, right? For rho of 0.009, my rho is 482.6. Any question on, I'm sorry, my mu over phi BD squared. Any question on that? Okay. So let me switch screens again. So there is the 482.6. See that? So that's where it came from. All right. So see how easy this is? All right. So this is very easy. From here, we did that, where the previous examples, you had to plug in numbers this big to get that. But again, you have to go through that to appreciate this, really. So if you have that, then mu over phi BD square equal this. My unknowns are b and d square. So I solve for that. BD square equal mu over that. You plug in the numbers. Again, one equation with two unknowns. You assume b and solve for d. So b and d, 16, 18, and 20. Okay? Somebody could say, how come in the previous example you did 12, 14, 16? Because this is a higher load. This is a bigger load. You can do that, but you probably have to modify your section. Okay? So you can start there, but then your section is going to be close to here. So again, we pick up the middle point. You don't have to do, you can pick this or that, anyone. Of course, we're going to round up this number. Okay, so this is B and this is D. So we're going to do D as 30.5. See, instead of 30.35, we're going to say 30.5 for D. Okay, so D is 30.5 and then B is 18. So in order to get the total depth for 30.5, I'm going to add 2.5 for that from center line to the bottom. So 2.5 plus this gives me 33. See, the previous example, I added 3 because I want to get a full inch of that depth. So now I can calculate the beam weight. Remember, I assumed the beam weight here. I assumed 400, but I have to check that. So what is the beam weight? Remember, I said we take the cross section of it, 18 times 33. There you go, 18 times 33. Divide by 144 times 150. That gives me this number, 618. Well, I assumed my load is 400. My load came out 618. Is that good? No. Not a good assumption. So I can revise my design now. Much greater than 400. So revise. Okay, when I revise, what do? I use this weight, assume this weight or close to it. So instead of assuming 400, I'm gonna assume now the beam weight as 650, close to this. So when I do that, well, look at, I calculate the dead load again. 1.2 dead load. Instead of 0.4, I put 0.65 because that's my new load. Plus 1.6 times live load. So this is my WU now. I calculate MU over phi BD squared equal this. Same thing. Okay, MU over phi BD squared. So this equation is, I don't have to go back to the table because my rho was still the same. So the 482.6 didn't change. Okay, what changed is M. So you plug this M here and find BD, this equation, BD squared equal this, 17,000. Notice that this was 16.5. Okay, so you solve for B and D, and then we're gonna pick up the middle one. And so we have to round up this. Okay, we're gonna have to round up this. Let's see how we do it. So instead of 30.9, we're gonna say 31. So if you make D 31, then that distance from center line of bars to the bottom is gonna be 3 because it makes this 34. See that? It's always gonna be either 2.5 or 3 to make that full depth as in a full inch. So our beam is B equal 18 by 34. The previous one was what? 18 by 33. So we increased it by an inch. All right, so then you figure the beam weight again. Okay, so 18 times 34, look at this, it came 637. 637 is close to 650, so that's okay. Especially you assumed your beam heavier than what it is, so you're on the safe side. You can go ahead and do another cycle. Assume the beam weight is 638, whatever, but it's not gonna be much difference, okay? So now I can say AS equal rho BD. Rho is 0.009, B is 18, and D is 31. This is the area of steel. Now you go to that table I showed you tonight for the group of bars. If you take 5 number 9 bars, your AS equal 5. Somebody could say, well, wait a minute, the AS is less than required. That's true. And you have to be very careful with that. And I'll show you what's going on. But somebody could say, oh, it's only 0.02 inches square. It's not a big deal. And it's a good assumption or judgment. Why? Because we magnify our load, 20% dead load, 60% live load. So can I cheat a little bit on the steel? Yeah, should be fine. But one thing you must do is check the moment capacity of this beam. Make sure it still can carry your moment capacity. And we're going to do that in a second. All right? So it says slightly less than required, so check the capacity of the beam. So A equal AS Fy over 0.85 F prime C times B gives me that. D minus A over 2. We know how to do that now. You can calculate phi Mn equal to this, and then is equal 623.9. What is my moment? I calculated my moment 623.4 as my applied moment. Look at this, the beam I just proportioned, it carries 623.9. Look how close it is, 623.4. It's still bigger, so it's fine, but it's very close. So in real life, I would not do that. I would definitely get a little bit bigger section because this is too close for comfort. Okay, but textbook-wise, it works, no problem. All right, any question? So this is that, and what we didn't do here is we didn't check the beam minimum. So you can go ahead and check the beam minimum. For example, you say, okay, for 5 number 9 bars, what is going to be my beam minimum? So you will do that, okay? Any question on that? Any question? All right. 4.5. So see, to answer the question somebody just asked, this is the way I would prefer you do this is the method. You assume the beam width, and then you do this method. This is the quickest way, so you don't have to calculate all these big equations. In the exam, I might tell you what this number is just to make your life easier, so you don't have to go through many cycles. So I might give you this number, all right? But this is the method I'd like you to use, and it's the most efficient method. But please, the examples, do them as he did, so you at least go through them one time. All right. The last example, 4.5. Select the reinforcing steel for the rectangular cross-section shown. So here, he's given me a cross-section. See? He's telling me the B is 16 inch, and H is 24, D is 21, and look at this guy again, 3 inches. It's either 2.5 or 3. So so all we have to do is how much steel I need here. Somebody could ask, when would this be the case in real life? This could be the case if this beam is exposed, that people can see that beam. It's a courtyard, it's an entrance to a hotel, and this beam is exposed, and then this beam is carrying something, whatever, and the architect would like it to be this size for some aesthetic reasons compared to other sizes around it. He tells you, he or she will tell you, I need 16 by 24. All you need to do is find how much steel you need in there. Okay? So that's this problem. Select the reinforcing steel for the rectangular cross-section shown, MU equal 160, and Kip's foot. So again, he gave me the MU. He didn't give me any other dead load, live load. Use a concrete 3,000, 60,000. Note that beam dimensions are given. The beam dimensions are given. Only AS needed to be determined. Now remember when we did our DT beam exercise, we were able to calculate the depth of the beam from the table. And we said that the width is half the depth. So our dimensions in the project are known now. So we can follow this example. We can follow this example because we know the dimensions of the beam. And if we did anything wrong, it's going to show when we check things. And I'll show you. All right? So this is how that works. We're going to do it 3 different ways. See, this worked 3 different ways. And you'll see this is going to show you kind of summary of what we've been doing. The first thing we're going to do is we're going to calculate MU over phi BD squared. See that? So MU is 160 because it's given. He gave me MU is 160. And of course, multiply by 1,000 and then 12 to get it in inch pound. Phi is 0.9, B is 16, and D is 21 from here. B is 21 and D is 16. So you've solved this 302.3. You're going to go to the appendix, table A12, and from there, you're going to read row. The one we just did, we used row and read MU over phi BD squared. Now we're going to use MU over phi BD squared and read row. Okay, you can go either way. You can go, you read row or you read that. Doesn't matter, whatever you have. Now, sometimes you're not going to hit the exact number. You're not going to find this exact number in the table. It's going to fall between 2 numbers. That means you have to interpolate. You know how to do that, straight line interpolation. But instead of doing that, just take the larger, just take the number next, higher to that. Because that's going to give you a higher row, a little bit higher row. And if you get a higher row, you're going to get higher steel. So that's fine. You're on the safe side. So you don't have to interpolate. Okay, look up the higher number. So this is the row. Look at this row, 0.5%. Remember we said row is around 1% always. So this is kind of low. This is kind of low. So AS equal row BD. And so this is that. You look at the table, 6 number 5 bars will give you 1.84 inches square, which is larger, it's fine. So again, you check the beam width for 6 number 5 bars, you're going to find that it requires 16.5 inches, the width. What is the width of our beam? Is 16. So we're okay. So we're close. 16 is, and it's 16 and a half. I can cheat a little bit. What's half an inch? Nothing. Right? So this is close. But if your beam is 16 and this is going to be 18, then that's bad. You go back and revise. All right? That's the first method. Second one is, look, using, instead of reading, look how easy it is. MU over this. Then the second method is you have to calculate rho. That's how we did the first example. And then you calculate Rn, and then you put Rn in rho, and look at all these calculations. See? Instead of doing all that, guys, that's why I said I prefer you to do this method. You calculate this and then go there. All right? So this is a good example because it refers you back to what we did at the beginning. This is the same value obtained by using the tables. So the remainder of the problem is the same. So meaning that once you get rho, then you're going to come here. Look how close it is. 538, 538. So after you do this, the rest is the same in here. That's the second approach. The third approach is an iterative method. Iterative method is that you assume A. Assume A is the depth of the compression block, and then you calculate AS, and then you find A is 2.62. See, here he didn't do it, but you're supposed to go back, because look, this is a little bit off. You're supposed to go back to this equation, and instead of putting 2, put 2.62 until the area of A matches with what you assumed, and then you find AS. But I don't like this method, so don't worry about that method. Some books you will have find that, so if you run across it, you know what that is. But you don't need to do it. The best method we like is this guy right here. Calculate this, go read rho, and then you solve it. Or get rho, and then you go ahead and find the other one. All right? So here it says close enough, and then this stuff like that. All right. That's it. The next, in the lecture next week, we're gonna start the one-way slabs. Okay, so that's why I don't want to cover it here. We'll cover it next time. All right. Any questions from anybody? Any questions, guys? Any questions? So again, you have all the data for the lab. So please work on that, and then start working on your lab report and your PowerPoint presentations, and do that. So in next class, now knowing these, how to design a beam, I am going to illustrate to you, because remember, these beams are simply supported. These are all simply supported beams. But our beams in the building is not simply supported. Okay? Is not simply supported. They are continuous beams. So let me do one more thing before we quit here. I want to plant the seed, what we're gonna do next time, but we'll do it for the whole class. So let me go to project. Okay. Just one more thing and we will quit. Where is that? Right there. Okay, so this is the PowerPoint for the beam, for the project. Remember, from this table we were able to calculate the depth, and then we did here. We got the depth. This for the slab. Let me go to the beam. We got the depth, and then we said the width is half of that. So we have our dimensions. See here, for our project, our beam is 14 by 26. So this is exactly similar to the last example we did that. The only problem is this is a continuous beam. It's not one-way slab. Okay? It's not one-way slab. So actually, let me illustrate it here. Actually, no, let me go to the DTB. So we ran this here and we found that this is our, see that? Okay. We found that this is our moment in the beam. All right? So, let me see. Okay, let me do it. First, we need to see how is this beam going to deflect. So let me show you how this beam is going to deflect. Under load, of course. So the exaggerated, this beam is going to deflect as such. Okay. Of course, exaggerated. This is the beam. We agree? That's how it's going to deflect. So from beginning, we've been saying concrete is strong in compression, weak in tension. And on the tension side is weak. We're going to put the rebars there so the rebars can help. So how are we going to do that? So I come here for this first slab. Look at the tension. Tension is at the bottom. It's being stretched. So I need to put the steel at the bottom. So the steel for this slab is going to be this yellow line. Okay? What about over the support? Look where the tension is at the top. It's being stretched at the top. So the steel is going to be at the top. We call that this is positive moment. This is negative moment. Same thing here. Stretching at the bottom. So the steel is at the bottom. Negative moment. Tension at the top. Same thing here. The bottom. Same thing here, the top. And then the bottom. Is that clear? So this is how we're going to put these rebars in the beam. Now, just another comment here. And we will talk about that. So what happened in here? Somebody could say, what about this? Well, here what we will do is we will add another bar in blue. And then we'll add another bar here. That bar will be insignificant. We just do it just to form a cage. Okay? So that will be added in there. We'll talk about that in the project. Okay? And that's going to be the reinforcement for our beam. In addition to that, what we're going to do is we're going to put the shear reinforcement. Shear reinforcement is going to be in here, just like that. That's chapter 8. Okay? That's chapter 8. And then all the way to the end. Okay, that's shear reinforcement. Is that clear? So this is how we put the rebars in the beam. But in order for me to know how much steel do I put here on this slab, how much steel, I need to know the value of this moment. How much steel do I put on top? I need to know the value of the moment here. How much steel do I need? I need the value of here. And then so forth. All right? Any question on this before I erase what I drew? Any question? Okay.
Just to confirm the
yes,
sure
sure
support. Yeah,
yes.
The shear supports are the stirrups, right?
Yes. Okay, yes.
Thank you.
Yes, the stirrups is what is going to resist the shearing force. That is going to try to break the beam in this action. Like, look at my hands. That's the shear. So the stirrup's going to do that. The longitudinal bar is going to resist the bending of the beam. Okay, that's what it is. Thank you. Any other questions? All right. So let me erase what I drew so we can go to the next step. Okay, so knowing that, I'm going to go back to the DT beam. See that? Look at the DT beam here. Remember we drew the shear and the bending moment? That's why. Because now, when I select the steel, I need to know these moments. So I come to the first span here. What is my moment? Here it tells you M max is 186, and look at these schematic. The maximum moment is here and there. So you know that value, 186.2 Gibbs foot. I already calculated my B and D, remember? I already calculated my B and D in this example. My B is 14 and D. H is 26, right? Can I calculate D? Yeah. If I assume this is 3 inches, so my D is going to be 23 inches. So D 23, B is 14. I will go here and I calculate mu over phi BD squared for this span. I know mu is 186, phi is 0.9, B is 14, and then D is, already forgot, D is 23. Okay? So mu over phi BD squared, I can find that value. I go to the table and I read rho. And then AS equal rho BD. That's the area of steel I need in this span. All right? Then I come to the support. What is my moment at the support? Look at this. From here, the maximum moment is here and there. 258. Forget the negative sign. We don't need that. So my moment here is 256. Again, mu over phi BD squared. Mu is 258. Phi is 0.9. B is 14. D is 21. I can find that number. Go to the table and read rho. Rho, once I get rho, AS equal rho BD. That's the area of steel I put on top. And then I come here to this span. This doesn't tell me what this moment is. Where are we going to get that from? Anybody? Where are we going to get this value of moment from? Somebody. Come on. It's okay to make a mistake, no problem. Where am I going to get this value of this moment? Because I need the maximum moment in this span here.
You take the integral of that section?
No. No. Where is this value? Where am I going to find this value? Come on, we went through this. It's okay. Anybody else? Okay, no problem. You're going to get this value by going to the numerical results. Remember? This is the graphical results of the program. You're going to go to the numerical result, look at span 2, and find what is the highest number for this diagram. You remember that? So that's where you're going to get this moment. Same thing for this. You're going to go to the numerical and find this. But due to symmetry, this value equal to that. And this value equal to that. All right? So that's the answer. And what about the negative moment? Where are you going to get this value? Anybody? Where are you going to get the negative moment here?
Same thing.
Same thing from the numerical results. Okay, so you're going to get it from the numerical results, but you're going to look at the support, not at the span length. It's going to be at the end of span 2 and beginning of span 3. That's where you're going to find that negative value. All right? So this is what we're going to do next week. I will illustrate an example with actual numbers so we can go through it and then show you that. And then with that, then you're going to go to your beam that looks like this now, and then you're going to select the steel fault. All right? So this is the beauty of coordinating the lecture with the lab, with the project actually, so we can continue doing that. Okay, any questions, guys? Any questions? All right. So that's it, but I'm going to take attendance if you don't mind. Let me get that. You can see we're covering a lot of important stuff, so I don't like people to miss classes. See, this is still Friday. All right. Let's see who's with us. Alexis?
Okay.
Alexis?
Yeah,
right there? Okay, thank you. Griffin?
Yeah, I'm here.
Brown? All right. Joycelyn.
I'm here, Professor.
Thank you. All right. Arba.
Here.
Thank you. Binyam. Binyam.
Here.
Okay. Adis.
Here.
Thank you. Gabriel. Mendoza. Okay, not here. Raymond Lamb.
I'm here, Professor.
Thank you. You missed last class, my friend, huh?
No. The last class I told you, I was like, you remember I sent you an email?
Oh, okay. You had an excuse there. Okay, got it.
Thank you.
Just to show you, I do show who was here and who wasn't. Christian, Sean.
Here, sir.
Thank you. Nicholas Craig.
Here.
Thank you. Min Wu.
Here.
Thank you. Bin Prado.
Here.
Thank you. Myra.
Here.
Thank you. Armando Carlos.
Here.
Thank you. So we have only one missing, which is Gabriel Paulo. Okay, no problem. Okay, that's it. Have a nice weekend, and then please do those examples before next Thursday, and I might assign a homework from this chapter. I will email it and post it on Beachboard. And remember, the homeworks 1 and 2 are due by next Thursday. I gave you a time extension on that. All right. Yes.
So I already submitted my work, but I feel like I kind of made a mistake. So
no problem. Go ahead, resubmit.
Okay, got it.
Yeah. Anybody wanna resubmit? No problem. And just make a note, please. Just tell me this is second submittal so I can ignore the first one.
Got it. Thank you.
All right. Anybody else?
So just to confirm, this is different from what you said. Is if we already turned in our work and we want to have that, then we're good then.
Yeah. If you're not happy with what you submitted, go ahead and resubmit. I will ignore the first one.
Okay, cool.
But
Thanks.
put a note on this new one. Say this is second submittal. Please ignore my first one. Then I can ignore that.
Sounds good.
No problem.
And also, also, is it on March 19th? I will not be here on March 19th. So,
okay.
Is there a possibility that I can sit in the Thursday night lab class?
Yeah, remind me. You have to email me, please.
All right, cool. I will.
Email me, and then I will reply to you.
Copy that. Thanks.
UCI email, please.
Got it. Thank you, sir.
Okay, thank you. Anybody else? Okay, have a great weekend, everyone. Please stay up on the class. Stay up with me, and we're covering good stuff. Don't fall behind. Have a nice weekend.
You too. Have a nice weekend.
You too. Bye-bye.